All right, for your third and final lecture for this week, we need to hit on the gas exchange physiology of respiration. So let's start with, oh, there we go. Pulmonary ventilation. So just as a recap, pulmonary ventilation just means breathing. So that's going to be your inspiration and your expiration. And both of those things combined is one breathing cycle. So there's a few pressures to keep in mind. There is an intra-alveolar pressure. So your intra-alveolar pressure is going to be the pressure inside the lungs, inside the alveoli. We also have an intrapleural pressure. And so in the last lecture, I talked about the parietal and visceral pleura and how it was important that those things maintain a pressure gradient. So the intrapleural pressure is the pressure between the visceral pleura and the parietal pleura. It is lower during inspiration, but that number always needs to be slightly negative compared to the outside air. And the reason is because your lungs need to be able to expand during inspiration. If that pressure wasn't negative, or if it was too negative, your lungs would always be overinflated. If it was positive, your lungs would be never able to inflate. They would be deflated. And so that intrapleural pressure is important to maintain that pressure between those two pleural layers in order to allow the lungs to inflate. Now it's all dependent upon recoil. So I talked about how the lungs, the alveoli, those bronchioles, everything recoils. And so that would be like during expiration. During expiration recoil, the visceral pleura pulls inwards. During expiration, the parietal pleura actually pulls outwards. And so they have these opposing forces between the two pleural membranes during expiration. So that would be an intrapleural pressure. So that's that pressure between the two pleural membranes at any given time. I'm not going to go too much further into the idea of intrapleural pressure. I'll give you an example here in just a little while. But the two major pressures that you're going to need to have a really good handle on is going to be the intraalveolar, so the pressure inside the lungs, and then the atmospheric pressure, which is the outside air pressure, which we call 760 millimeters of mercury. Okay, so you have this atmospheric pressure on the outside air pushing on your lungs. You have at rest, you have an intraalveolar pressure also of 760 on the inside, and this is at equilibrium. We're going to talk about when these things are not at equilibrium, which is during inspiration and expiration. Something to note is that air depends upon Boyle's law, and this is going to be different than the bloodstream. So we mentioned last week and the week before that as the volume of blood increases, your pressure increases, right? So they're directly related. Well, for gas, it's going to be an inverse relationship, just to confuse you a little bit more, right? So as your air volume increases, that actually decreases the pressure and vice versa. So if you think about a syringe, and you pull back on the plunger of that syringe, you are increasing the volume of air in that syringe. And as you're increasing that volume, you're decreasing the pressure. It's pretty easy to pull back on that syringe, right? Well, if you push that syringe plunger up, now you're decreasing this volume of air. And you can feel the increasing pressure as the air goes out of the syringe. And so that would be an increase in pressure, decrease in volume. So imagine no air movement for a second. You're not breathing, right? The pressure inside the lungs is essentially equivalent to atmospheric pressure. Now, we know that we need to breathe, right? And so those pressures have to change. And so during a breath in, okay, when you take a breath in, and we're going to go over this more in just a second, you are increasing your thoracic volume. Okay, your thoracic cage expands. And if you're increasing that volume, you're decreasing the pressure inside your lungs. And that's inspiration. That's what allows us to take air in. Now, on the contrary, as we exhale, we are contracting our thoracic cage. We're contracting that volume. And so that pressure is going to increase and force air out. Okay, so it's just like this plunger, if this was our thoracic cage. We're going to go over these again. So inspiration, here's your steps. So the first step is skeletal muscle contraction, particularly the diaphragm. So your diaphragm sits right under your rib cage. During inspiration, your diaphragm contracts, and this is where students get really confused and lost. But when the diaphragm contracts, it actually moves down. And so a lot of students think that it should move up if it's contracting, but that's not the case. When the diaphragm contracts, it actually moves down. And as the diaphragm moves down, okay, it's pulling the rib cage down. At the same time, you've got muscles in between your ribs that are contracting and pulling your ribs out this direction. So now we're pulling from this direction, and we're allowing our rib cage to expand from all directions. Okay, so we have increased that volume. Now, if we increase the volume, okay, pressure is going to decrease. So what you just did by increasing that volume is you decreased the pressure in your lungs to 758, which 758 is lower than atmospheric pressure. This doesn't change. This is 760. So air moves with a concentration gradient, just like blood, okay, and solutes. So it's going to move from a higher to lower concentration. So it's going to move from the area of higher concentration, which is outside, to the area of lower concentration, which is inside. And that allows you to take air into the lungs. Air is going to move into the lungs. That's inhalation or inspiration. Okay, here's that intrapleural pressure. I'm not going to focus too much on this. But essentially what it needs to always be is something less than atmospheric. Okay. Now, expiration, okay. Now the diaphragm is going to relax, and when it relaxes, it's going to come back up to its normal resting position. Your intercostal muscles in your ribs are going to relax, and so your rib cage is going to come back down, okay, or recoil there. So you're decreasing your thoracic cage volume. Atmospheric doesn't change, it's always 760. If you decrease your volume, your pressure goes up. And so your pressure is now going to be slightly higher than atmospheric, and gas moves from an area of high to low concentration. So air is going to move out, and that's expiration or exhalation. Okay. So students get confused because they don't think about this first couple of steps, the skeletal muscle contraction. Think about what's happening during taking a breath in and a breath out in terms of muscle contraction and what that does to the volume of the thoracic cage. After that, you just have to think opposites, right? So as the volume decreases, the pressure increases and vice versa. And here's what this looks like. Here's a figure from your book. So at rest, essentially these pressures are going to be equal. Notice how your intrapleural pressure is slightly negative, right? It always needs to be slightly negative compared to your other pressures. Now, during inspiration, okay, your diaphragm is going to move out, your thoracic cage is going to move out, and therefore increase this volume in your chest cavity. And so if the volume is increased, the pressure decreases below atmospheric. And so you're going to be at 758. And that allows air to draw into the lungs. Remember, air is going to move from an area of higher concentration, which is 760, to an area of lower concentration, which is 758. Then when you exhale, okay, this thoracic volume is going to shrink again, go back to, it's going to recoil, and decreasing that volume is going to increase the pressure. And so the pressure is now is 762, and that's going to force air out. And then between each breath cycle, there's this pause of no air movement where the pressures will be equal for just a second. Now your skeletal muscle contraction, what causes this to happen is by your nervous system. We'll talk about that. So here's your clinical correlation. So what happens if that intrapleural pressure is too great? So remember I said that this intrapleural pressure has to be slightly negative compared to the other pressures. But what if it's not? What if it's too high, right? Then what happens? Well, you have a higher volume of air pushing on that lung. And so if you have a higher volume of air pushing on that lung here, okay, this lung is going to collapse. We call that a pneumothorax. That pressure is going to push on that lung from this direction. So what that's usually treated with is a chest tube. What the chest tube does is try to equalize the pressure here between inside and outside. And then some of this intrapleural air will get reabsorbed. And so it will eventually take you below that atmospheric number. But the idea is to kind of equalize it first, take the pressure off the lung to allow the lung to inflate again. And then the lung and pressures will kind of even out to its homeostasis again on its own over time. So usually diagnosed with an X-ray, treated with a chest tube. And this would be a case of positive intrapleural pressure. So that pressure always has to be a little bit negative, but what happens if it's too positive? Okay, so we know that we are able to take a bigger breath in than usual and a bigger breath out, right? So I talked a lot about the diaphragm and the intercostal muscles, allowing that passive respiration to occur, but you're going to engage more muscles the deeper breath that you take. And so inspiratory muscles, if you all just sit here and take a really deep breath in, what muscles are you thinking that you're using, right? Where do you feel engagement, muscle engagement? Your erector spinae, which are in your back, your sternocleidomastoid and your scalenes, which are going to be in your neck, your pec major and minor, which are going to be in your chest, and then your serratus anterior sits like under your armpits. And then you do have different types of intercostal muscles. You're going to engage more of them, called your internal intercostals. Now, I want you to exhale forcefully and see where you feel muscle engagement, right? You're going to feel a lot of it in your abdominals. So your rectus abdominis, your obliques, and those abdominal muscles that way. Now, how is breathing controlled? So it starts with muscle contraction. That comes from your brainstem. Your brainstem sends signals down to those skeletal muscles to tell them to contract more often or less often, according to what the cellular requirements are of the body. Do you need more oxygen? Do you need to expel more carbon dioxide? What's going on? So it's in the brainstem. We're going to get to that in just a second. It's rhythmic. So you have a pattern of breathing that your body kind of follows. You can adjust the rate and depth of your breathing to meet your cellular requirements. So sometimes if you're sitting here passively breathing and all of a sudden you just feel the need to take a deeper breath than normal, just one, that was your brainstem detecting a change in your blood composition, indicating that you needed to take in more oxygen and expel more carbon dioxide in that breath. Your nervous system can stimulate or inhibit skeletal muscle contraction according to how you need to breathe, faster or slower. You can do this consciously, but it also happens unconsciously. That's why you cannot ever die from holding your breath on your own, right? And it's highly dependent upon pH detection. And your brainstem does pH detection. What I'm going to talk about in just a little bit here, and I talked about it week 1, is carbon dioxide having acidic properties. So the more carbon dioxide that you have in your bloodstream, the more acidic your pH is going to be. And so let's just think for a second about holding your breath underwater. Why can you not hold your breath forever, right? Because your pH is going to go too low. The longer you hold your breath, you're holding that carbon dioxide in and you're not breathing it out. And the longer you hold that in, the more acidic it's going to make your body. And so then eventually your body's going to tell you to exhale it and breathe. Same with hyperventilation. So if somebody's breathing really fast, they are breathing out too much carbon dioxide. You have to have some carbon dioxide at any time to keep your pH normal. So why do we have people breathe into a paper bag? Well, we want them to breathe in some of that carbon dioxide because they're getting rid of too much. Okay, and that will bring their pH back down to a normal. Okay, so think about carbon dioxide in terms of pH. Here's a good schematic from your book. This shows negative feedback. So if you have decreased ventilation, so let's just say you're holding your breath, what happens is you're holding on to more CO2, more carbon dioxide. That's going to lower your blood pH and increase the amount of carbon dioxide in your blood, obviously, right? And you're going to have a lot of neurons all over your body detecting that pH change. It's going to send a message to your brainstem, and in an effector, it's going to tell your skeletal muscles to breathe faster and maybe even deeper. And then as your ventilation increases, okay, that carbon dioxide will be exhaled and your pH will return to normal. And that's how the negative feedback occurs. Then you'll just begin to breathe normally, right? Negative feedback. So your rate and depth of breathing is handled by your brainstem here. So here's your brainstem, here's your pons, your midbrain, your medulla. We're going to focus here on the pons and the medulla oblongata. There's a ventral group and a dorsal group. Your ventral group has different neurons that are going to handle inspiration and different neurons that are going to handle expiration. And basically your dorsal group just tells your ventral group what to do. So your dorsal group will tell your inspiratory neurons to either fire or not fire, or tell your expiratory neurons to fire or not fire, depending on if you need to breathe in or breathe out, right? That's in the medulla. In the pons, that has control over this group here, over the medullary group, and your pons responds particularly to abnormalities in like emotion, physical activity, things that don't have to do with breathing and just a normal resting. If you need to breathe more deeply or increase your rate due to extenuating circumstances, essentially. So I'm not going to go into too much detail here, but just know that your medulla and your pons are responsible for controlling inspiration and expiration. And as your inspiratory neurons are being stimulated, your expiratory neurons are being inhibited, and vice versa. So as you take a breath in, the neurons that assist with breathing in, including the neurons that tell the diaphragm to contract, move down, right? Those neurons are firing, but your expiratory neurons are being inhibited. Now, when you exhale, now we're going to tell the diaphragm to stop contracting. So these neurons are going to be inhibited and these ones are going to be firing. It's a very crazy balance and cycle. It happens so fast, and it's truly fascinating. So a clinical correlation here would be apnea. So there's different types of apnea. There's something called central apnea, and there's obstructive sleep apnea. Obstructive apnea is the one that you probably all think about when you have somebody who snores, can't breathe super well when they're sleeping. Maybe they're on a CPAP machine here. That's obstructive sleep apnea. So here's an example of obstructive sleep apnea with the tongue and all of kind of the muscles here pinching off the airway, which causes that snoring situation to happen. That's obstructive apnea. Now, apnea is dangerous because it can be dangerous over time because you're not getting enough oxygen with each breath. Hypoxic symptoms can be, fatigue because you just, your brain is basically deprived of oxygen, headache, those types of things. So a lot of people who have sleep apnea that don't wear CPAP do have a lot of those symptoms. The other type of apnea is central sleep apnea, or central apnea rather. This is actually an issue with the respiratory control center. So this is a brainstem problem. This one is more common in infants. This is thought to be a major cause of SIDS, sudden infant death syndrome. Interesting story, my 3-year-old nephew had both of these at birth, and they were kind of an incidental finding. He was a healthy pregnancy, full-term baby, but he had temperature issues, when he was born. And so he got sent to the NICU. And if he hadn't gotten sent to the NICU, he would have never had these diagnoses probably in time. Because once you get sent to the NICU, in order to go home, those babies all have to pass a car seat test where they sit in their car seat for a period of time, and their oxygen trends are monitored for like, I think it's like 2 to 3 hours or something like that. Well, he failed. Okay. And his problem after, oh my gosh, tons of sleep studies and tests and everything else, they found that he actually had central sleep apnea and obstructive sleep apnea as a baby. My sister, actually, after they went home from the hospital, she had to do CPR on him on the side of the highway because she was driving home and his monitor went off. Now, he had that monitor because he had been in the NICU, but if he hadn't have had that monitor, she would have never known and she could have lost him. A lot of the doctors are saying that he would have been a SIDS baby. So very, very interesting area of study for sure. He has since grown out of both of his apneas. He grew out of the central apnea first, and then he just had his tonsils out last year. And so now he's grown out of that obstructive one as well. Okay, so we know that gases move from a higher to a lower pressure. Different gases make up the total mixture of air. We call that partial pressure. And so we know that air is consisting of like nitrogen, carbon dioxide, oxygen, and they each have a partial pressure. And so air is 21% oxygen. And so if we take 0.21, which is 21% as a decimal, times it by the pressure of air, atmospheric air, which is 760, the partial pressure of oxygen is 160 millimeters of mercury. We could do that for all of the other gases that make up the air. That's partial pressure. Keep that in mind. Now, factors that affect breathing, what your partial pressure of oxygen is, what your partial pressure of carbon dioxide is, and that's atmospheric or in your body or both. Your concentration of hydrogen ions, we're going to get to that. What emotional state you're in, are you stressed, right? Is your body going through fight or flight? Physical activity, the more physical activity you have, the more demands your body has for oxygen intake and carbon dioxide exhalation. And how far your tissue is stretching. If your lungs are stretching too far, right, your body will bring that back to a normal and decrease your breathing. So recall that gases move from an area of high to low concentration. That's their gradient. So interesting concepts here. So blood entering the alveolar capillaries. So think about that for just a second. If you have blood entering the alveolar capillaries, which are the capillaries that encompass the alveoli, that blood is coming from the pulmonary arteries, right? Because our blood going to the lungs comes from the right side of the heart, deoxygenated blood, right? So that blood entering those capillaries coming through the pulmonary arteries to the lungs to pick up oxygen has a partial pressure of carbon dioxide of 45 millimeters of mercury. The alveolar air has 40 millimeters of mercury, right? So the air that you breathe in has a higher concentration of oxygen, which we're going to get to, than carbon dioxide. And we know that that deoxygenated blood came from your systemic tissues, right? Because that carbon dioxide got put into the bloodstream as waste and then goes to the lungs to be exhaled. So because the partial pressure of oxygen in the bloodstream, or excuse me, carbon dioxide in the bloodstream is higher than the alveolar air, the carbon dioxide will move from the bloodstream to the alveoli and then be exhaled out of the lungs. Oxygen now, okay? So blood entering those capillaries is deoxygenated blood. It's got a partial pressure of oxygen of 40. The air we breathe in is high in concentration of oxygen, high in partial pressure of oxygen. It's 104. So you can imagine that oxygen is going to move from our lung alveoli into the bloodstream, and that is how our blood gets oxygenated. Then that oxygenated blood will go back to our heart, the left side of the heart, and be pumped out to the body. Okay, here's a good picture. So here's your blood flow from your right ventricle. And we know that the right side of the heart pumps deoxygenated blood. So you're going to have a higher level of carbon dioxide than you do oxygen. So if this carbon dioxide level is 45, the alveolar carbon dioxide has to be lower because we want to drop off that carbon dioxide at our lungs to be exhaled. Oxygen is low compared to our alveoli because if this is deoxygenated blood, we need to oxygenate it. And so we want oxygen to move into the bloodstream. So the air you breathe in out here is 104. It's going to move from high to low. So it's going to move into the bloodstream. So now we're oxygenated blood over here, right? And so our CO2 has gone down because we have dropped some off in our lungs to be exhaled. And our oxygen level has gone up significantly from 40 to 104. And now we're oxygenated blood. We're going to go back to the left side of the heart and we're going to be pumped out to the body. This is in the lungs. Okay. Now we're going to talk about what happens at the systemic area next. So oxygen transport. How is oxygen transported through the bloodstream? 98% of it is bound to hemoglobin. We talked about hemoglobin when we did blood. 2% is dissolved in plasma. Hemoglobin is heme, which is your iron containing molecule, and your globin, which is your protein. When oxygen is bound to hemoglobin, we call it oxyhemoglobin, and each hemoglobin molecule can carry 4 oxygen molecules. It's got 4 heme groups. Each heme group can bind 1 oxygen. How much oxygen there is in terms of partial pressure determines how much hemoglobin is going to bind. So the higher the partial pressure of oxygen, the more of that oxygen is going to be bound up to hemoglobin to be transported through the bloodstream. It's very efficient. And so it can be illustrated here by a saturation curve. So the higher the partial pressure of oxygen, the more saturation you're going to have here. Interestingly about here, things start to taper off, but you can have 100% saturation of hemoglobin. Thinking about that, you can be oversaturated with oxygen, right? Your hemoglobin molecules can only carry so many molecules of oxygen. At some point, some of that oxygen will not have the chance to bind hemoglobin. And so if you have too much oxygen in your body, right, people maybe who are on supplemental oxygen who don't need it, now they just have all this extra oxygen in their bloodstream that isn't being utilized. It's not traveling on your red blood cells and hemoglobin. It might be dissolved in plasma, but it's not traveling on hemoglobin. Interestingly, 75% of your oxygen is actually retained at any time. So we always talk about venous blood being deoxygenated, but it has oxygen. It's got 75% oxygen actually. Only about 25% of your oxygen comes off of the hemoglobin molecules. And that is important because our body needs a reserve of oxygen at any time. We never want to be at 0. We never want to be at 0% oxygen. So it's just deoxygenated in comparison to your arteries. Here's a good picture of what happens at the alveoli and then again at the tissue level. So we talked about this, where oxygen moves from an area of high to low concentration. So it's going to move from the alveoli to the red blood cell in the bloodstream. Carbon dioxide moved the other way. Now, systemically, the oxygenated blood goes out to your tissues. We know that oxygen gets dropped off in your tissues, which means that your tissues have to have a lower concentration of oxygen than your bloodstream. Notice how some of that oxygen decreases naturally here from 104 to 95 as it's traveling through the bloodstream. But once you get to your tissue here, you're still at 95 partial pressure and your tissue's at 40. So this oxygen is going to be dropped off in the tissues. If we add carbon dioxide into this image, your carbon dioxide partial pressure would be high here compared to here. And so your carbon dioxide would go back in there, travel back to the lungs, carbon dioxide is dropped off, oxygen's picked up, and the cycle goes all over again. So carbon dioxide is transported a few different ways. So back to oxygen, all of it, almost nearly all of it is on hemoglobin. Carbon dioxide, a lot of it's bound to bicarbonate. Some of it's bound to hemoglobin. It binds to a different area. It binds to an amino group on hemoglobin, so it does not compete with oxygen for binding groups on hemoglobin. So that's a good thing. A lot of it's bound to bicarbonate. So if you can recall this equation from week 1. So carbon dioxide plus water goes to carbonic acid, which dissociates into hydrogen ions and bicarbonate. Hydrogen ions are acidic. Bicarbonate is a buffer. Okay, so carbon dioxide jumps on our red blood cell. There's water in the cytoplasm of that cell. Okay, so that carbon dioxide from our tissues jumps on the red blood cell. It needs a ride back to the lungs, right, to be exhaled. Well, while it's being carried on that red blood cell, it may combine with those water molecules. And then this reaction is going to go forward. So it's going to become carbonic acid, which quickly dissociates into hydrogen ions and bicarbonate. Bicarbonate leaves the red blood cell and hangs out in the bloodstream until it's needed. It's a buffer. The hydrogen ions will hang out on the red blood cell. Hydrogen ions do compete for binding sites with oxygen. So kind of one or the other has to bind hemoglobin, essentially, which also makes hemoglobin a buffer as well, because it can bind those hydrogen ions. And if this is deoxygenated blood, those hemoglobin ions are not full of oxygen, right? So they can then bind with hydrogen ions in the meantime to kind of control that pH of that red blood cell at any time. So a lot of that carbon dioxide is going to be bound up to bicarbonate here, and then this reaction can go the other direction as well. So here's a clinical correlation for you. So during exercise, right, proprioceptors, which are receptors that detect movement, send signals to the respiratory center. Your respiratory center tells you to breathe faster and deeper than normal. And by doing that, it's telling your respiratory muscles to contract faster, more often. Why? Because our brainstem detected that our muscles are producing a lot of waste carbon dioxide because they're moving a lot and they need more oxygen to do their cellular requirements, to make ATP. Your brainstem, you have a blood-brain barrier between your blood and your cerebrospinal fluid. Hydrogen ions cannot cross that barrier, but carbon dioxide can. Your brainstem is more likely to react to high levels of carbon dioxide rather than low levels of oxygen, if that makes sense. And they should be inversely related. So if you have high carbon dioxide, your oxygen level's low. And once that carbon dioxide is in that cerebrospinal fluid, which is the fluid that kind of surrounds your brain structures, it can combine with water and form the hydrogen ions, which can change the pH of that CSF. And then that's what triggers your brainstem to increase your breathing rate, to breathe out that carbon dioxide more often so that you don't have that buildup of hydrogen ions. Okay, I know that's kind of a complicated scenario to imagine, but your book goes into really good detail with this. And if you have any questions, just let me know. So that kind of ends up our physiology section and our respiratory for the week. Just let me know if you have any questions.